Welcome to Chapter 19, Fuel Pumps, Lines, and Filters. In this chapter, we're going to discuss the entire fuel delivery system, everything from the fuel tank all the way up to the fuel rail itself. So first things first, the fuel tank. The fuel tank's job is fairly straightforward. Its job is to hold the fuel that's needed in order to drive the vehicle. Fuel tanks come in different sizes. Typically, fuel tanks will allow for a capacity for 400 to 600 miles worth of driving, and so the fuel tank size is generally dependent on the fuel economy of that vehicle. So if you had a big pickup truck, for example, it's likely going to have a fuel tank that's closer to maybe 30 gallons in size, versus a small Toyota Prius that gets great fuel mileage. It might have a fuel tank that's only 10 gallons, and so the size of the fuel tank is generally directly related to the fuel economy of the vehicle. Manufacturers used to use steel, so they use a steel metal type fuel tank. The problem with that is steel fuel tanks rust, and so over time manufacturers have gone away from steel fuel tanks and they've moved into more of a plastic type composite fuel tank in order to eliminate the corrosion and leak issues. So one of the things we need to consider with the fuel system is the fuel system's job is not only to allow the engine to run, but we also have emissions control devices that are on the fuel system. So the federal government, the EPA, requires that we keep our evaporative emissions under control. And so evaporative emissions are the fumes. When you go to the gas station and you fill up, you can smell the gasoline. Those are fuel vapors, and those fuel vapors have to be kept under control and retained. They cannot be allowed to just off gas into the environment. And so the fuel system itself on a vehicle is there to deliver fuel, but we also have to be mindful of emission type controls and also safety. So moving on to the next page here, we take a look at the top page 239, figure 19-3. Figure 19-3 illustrates a check ball, this green ball that's right here. On the note of safety, manufacturers have to do a few things and keep a few things in mind when designing a fuel system on a car. So, rollover protection. If a car is in an accident and it ends up on its roof, you have a fuel tank that's upside down, and you have to have some sort of means to keep the fuel in the tank and prevent the fuel from leaking out onto the concrete. So you can imagine the fireball that would ensue if you had an open fuel line. Let's say somebody left the cap off the filler neck. It happens. So let's say somebody accidentally left the cap off the filler neck and the car was in an accident and it rolled over. The cap is like the secondary means to prevent fuel from leaking out. The primary means is this check ball itself. So that check ball will move up into a position. If it were upside down, it would move into a position that would seal off the filler neck itself and prevent fuel from leaking out. Onto the filler neck, figure 19-4. The filler neck serves two purposes. The first purpose is fairly obvious. It's to allow you to refuel your tank. So when you pop the door open on the side of your vehicle and you take the cap off, you have access to the fuel tank. So you put your fuel nozzle in and you fill the tank up on this lower hose. The second hose is actually an evaporative component. And so when you're refueling the vehicle, you're disturbing that fuel and you're causing it to tumble around and you're creating vapors. That second tube is there in order to help capture those vapors and draw them into the fuel canister, the charcoal canister that's in the fuel tank itself. Or not, if it's not in the fuel tank, it's somewhere near the fuel tank. It's an evaporative type emissions control. Figure 19-7 illustrates the inertia safety switches that are found on Fords. So manufacturers have a few different ways they control the fuel pump during an accident. And so if you can imagine a car gets into an accident and a fuel line is ruptured. If the fuel line is ruptured but the key is not shut off, there has to be some sort of way to prevent that fuel pump from continuing to run. And so manufacturers have designed a few different systems. One of them is the Ford style, which is an inertia switch, and inside this inertia switch there's like a steel ball that sits on 2 contact points, and in normal operation that steel ball just lays there and it completes a circuit. In an accident, with enough G-force, that steel ball will actually pop out of its position, and it'll cause an electrical open situation on the fuel pump itself, shutting off power to the fuel pump, which then shuts off the fuel pump. The other way manufacturers control fuel pumps during an accident is by monitoring engine RPM. And this is actually the most common way manufacturers do this, especially on our more advanced cars. In the last couple decades, everything switched over to computer controls. So what manufacturers will do is they'll actually watch the engine RPM. So the crankshaft position sensor is making a signal as the engine's running. And if you were in an accident and you ruptured a fuel line, with the lack of fuel, the engine would stall. And so when the RPM goes to 0, there's a period of time, maybe 2 seconds at most, where the manufacturer will allow the fuel pump to continue to run without a crankshaft position sensor signal, and then it'll shut off the fuel pump. And so there's a few different safety features, a few different ways manufacturers do this, and this just illustrates one of them with the inertia, and then my example with the monitoring of the engine RPM. Fuel lines. Manufacturers still to this day use steel fuel lines for the most part. There are plastic lines that are out there on the undercarriage of a car, but typically on the underside of your vehicle you're going to see steel fuel lines. It doesn't matter if it's a Ford or a Chevy or whatever, Chrysler product. The issue with using steel, though, is we have to have at least a flexible link at the engine side and a flexible link at the gas tank side. And so if you think about an engine that's running, an engine moves. It likes to rock back and forth as you accelerate and deaccelerate. And so we cannot have a steel line that is affixed to the frame without any type of flexible nature to it as it goes through the engine. And so what manufacturers will do is they'll actually, from the steel line, just at the end of the steel line, as they're getting close to the engine, they'll switch it over to a plastic line. They used to use rubber in order to create that flexible link, but the problem with rubber is it dry rots. And so the dry rotting causes safety issues, for one, and it also causes emission issues if it starts to leak. So plastic lines have become the main flexible link in the system. Most manufacturers utilize that. Some manufacturers will still run some manufacturers run a plastic line from the tank all the way up to the engine, and then what they'll do to protect the fuel line on the undercarriage of the car is they'll put some sort of plate that you have to unbolt and remove. It could be plastic or it can be a steel cover of some kind. But you can't have a plastic or a rubber line exposed to the undercarriage of the car because of road debris. So if you had something kick up underneath the car and you had a plastic or a rubber fuel line, that fuel line could become ruptured if it were hit by something. And so when manufacturers have exposed fuel lines under the car, they tend to be steel. If they're protected, they may have a plastic fuel line. And the nice thing about the plastic fuel lines is they don't rust. And so you'll get used to this as you're working. You'll be replacing a lot of fuel lines, a lot of brake lines because of rust. We live in the salt belt, and so it's a common issue. Typically, when you see the first brake line go out, you might as well replace the fuel lines too, because generally speaking, they're right behind each other. They'll go out at about the same time. So page 243 and 242. Page 243 and 242, we're going to discuss quick connect fittings. So in the past, manufacturers would actually use a thread together type fuel component. So the fuel line itself would actually thread together. Manufacturers have gone away from that style and they've gone to these quick connects. And so there's a couple different pictures here. All the quick connects they're a one-time, I shouldn't say one-time, they just click together. There's like a special shark fitting type component inside of the line connector that when you shove it together, the little fingers come out and it prevents the line from separating. It makes it really easy for manufacturers to assemble. It eliminates cross-threading, which would slow down production. You know, if you had a person on the line that was assembling these components, if they were to cross-thread something, or just the fact that they have to sit there and use wrenches and thread it together, it's time-consuming. And so manufacturers have gone to quick necks. The problem with quick necks is you have to have special tools in order to get them apart. It's not that big of a deal. You can buy a master disconnect set. It's something that you all need to consider doing sometime here in the near future. This is one of those tools that you don't have to run onto the Snap-on truck. You don't have to go spend big money on a master disconnect set. You can buy something on the internet that's relatively inexpensive, because most of these tools are just plastic. Some of them are metal, but they're not intricate, and there's nothing really special about them that would justify spending a whole bunch of money on them. So if you were to spend $50, you could probably get a pretty decent line disconnect set. And so the general principle, I'm going to show you some, I'm going to show a video on this as well. I can't do an illustrate, or I can't demonstrate this for you. So I'm going to have to show you a video online. But the general way these work is in order to get them disconnected, this step one here, okay, step one is twisting, step two is blowing a little bit of air in there. That's generally not needed. You know, if you've got a vehicle that's really dirty, that's why they're saying blow the air out. But steps 3 and steps 4 are the most important part. So what you need to do is actually shove the two ends together and then shove this quick disconnect tool inside the fitting. And when you do that, you're going to push the little fingers out of the way that are keeping that line together. And once that tool is installed, you can then pull out on the other line and separate the two. When putting them back together, it's always a good idea to have some sort of lubrication, because there's O-rings on the inside. So the pipe has this pipe fits down in there, and the only thing that keeps the seal is O-rings. And so if the O-rings are dry and you go to install this, what you can actually do is damage the O-ring and cause a leak. And so a question people ask me a lot of times is, what type of lubrication do I put on it? Well, here's the thing. If you're doing a fuel filter, for example, and you have to get out this disconnect set, you have fuel leaking everywhere. Just take some of that fuel and wet the fitting, and the fuel itself will be enough as a lubricant. You can use PB Blaster, you can use a little bit of engine oil, pretty much anything that's laying around other than like brake fluid. Don't ever use brake fluid on something like that. But it's pretty straightforward. It's not that big of a deal. They can be a little intimidating when you haven't seen a certain style, because like Ford uses one style, GM uses another, Honda uses another. And until you've gone through and actually disconnected every manufacturer's quick connects, you could struggle with them a little bit. But once you get through it once or twice, it'll become second nature for you. So let's move on to fuel pumps itself. We're going to talk about fuel pumps, and then we're going to talk about the entire sending unit, or the fuel pump module. So fuel pumps are pretty straightforward. On the inside of a fuel pump, you have an armature that's spinning, and you have a pump that's connected on the shaft, and the pump is going to look something like this. And so pumps are pretty straightforward. We've discussed pumps many times. They can come, there's no like one exact style pump that manufacturers use on a fuel pump, but the purpose of a fuel pump is to draw fuel into the pump and then compress that fuel. And at the same time as compressing the fuel, it's pushing the fuel. So we're creating pressure and we're creating volume. And those two things are very, very important, because when we go to diagnostics and we start talking about testing fuel pump systems, we have to keep in mind that just because we have pressure doesn't mean that we have good volume. And just because we have good volume doesn't mean we have good pressure. And so if a manufacturer specs out, like let's say 1 liter per minute of fuel, that would be considered volume. If they spec out PSI, that's the pressure side. And so if a vehicle needs 1 liter per minute minimum of fuel flow, and it needs to be able to maintain that 1 liter per minute at 50 psi, those would be the specs that we would hold that fuel pump to while doing diagnostics. Fuel pumps used to be just on off, and so this is an important part that we need to discuss in this chapter. Fuel pumps used to just be supplied battery voltage, and so you had a relay that turned on a power supply to a pump, and the pump ran at one set pressure the entire time. We would regulate the fuel pressure via a fuel pump, via a fuel pressure regulator. And so we would send maybe 80 psi to the regulator, and then the regulator would allow the 50 psi to the engine that the engine actually needed, and it would dump the rest of that fuel back to the tank. It's a pretty crude system. It worked very, very, very well for a long period of time, but manufacturers have gone away from just a simple on-off fuel pump, and they've moved to the pulse width modulated fuel pump design. And so if you think about what pulse width modulation is, that's controlling the on-off time of the fuel pump. And in doing so, we can control the speed of the fuel pump. And by controlling the speed of the fuel pump, we can control the pressure and the volume. And so you might ask, why would manufacturers go away from just a simple on-off if it works so well? You have to think about what's going on in engine technology. We've talked about engine tech advancing multiple times. Engines nowadays have power bands that can change on demand. And so we've got turbocharged engines, supercharged engines, we got variable compression ratio stuff, variable valve timing stuff, and we can literally change the power flow of that engine on demand. Well, that means is we have to have a fuel system that can also change fuel delivery on demand. And so manufacturers now incorporate a fuel pump that is pulse width modulated, and it's directly fed its pulse width by the computer's demand. And so if you're under wide open throttle on a turbocharged direct injected engine and you're trying to build 300 horsepower, that fuel pump is probably going to be on at like 98% duty cycle, meaning that it's pretty much on 100%. But now as you're running lightly down the road and you only need 30 or 40 of that horsepower, that fuel pump is going to be pulse width modulated much slower, and that eliminates the need for other complex. I mean, it's very difficult to control fuel on demand like that unless you have some sort of pulse width modulated pump. And so the testing procedures are a little bit different, but it's actually kind of nice because now in your scan tool you can actually cycle these fuel pumps up and down. So all right, this illustration right here at the bottom of page 246. This illustration, 19-16, is a typical fuel pump module assembly. The book talks about fuel pump modules in a couple different locations. I'm just going to pull this picture up because this is an actual component. To me, it looks like it's a General Motors product. It might not be, I don't know. But this sending unit is, I'm calling it a sending unit. It's a fuel pump module, so I should just stick to what the book calls it. The fuel pump module assembly is replaced as one whole assembly. In the past, you could replace just a fuel pump. On vehicles from like the mid-90s to current, you cannot replace just the fuel pump. So if you had a car that came into your shop that was a crank no start, for example, and you did some tests on it and you realized that, hey, this fuel pump is not putting out hardly any PSI, or it's not even turning on. In the past, what you would do is you'd order up just the fuel pump, and you would take the fuel tank out of the vehicle, you'd pull this similar looking component out, and you would take just the fuel pump that's located down here, and you would unhook it, and you'd pop a new fuel pump in, and you'd put the rest of this assembly back together. Well, manufacturers have gone to this like one-time use, like it's one and done. And so there are other components that are built into this fuel pump module that are not serviceable. So the fuel pump's not serviceable, the float arm, the sending unit for the fuel level, none of that stuff is serviceable. And so when you have a car that comes into the shop nowadays and you have a fuel pump issue, you're going to have to replace this entire module. It can be expensive. It's not uncommon for a fuel pump module to be $700 for the customer, or a fuel pump itself on a 1980s vehicle might be $30. And so another issue with the fuel pump modules and the way manufacturers are going is they're now incorporating the fuel filter in there as well. And so if you have a situation where you just have a clogged fuel filter, you have to replace this entire module. You cannot get in there and just replace just a filter. That's becoming more and more commonplace. Why manufacturers are doing this, it drives me crazy. There's really no reason for it other than simplifying the manufacturing process and then forcing people to buy very, very expensive components when they do experience a failure. So if you had a customer that came in with a car that had a fuel pump module like this, and the only thing that was wrong with it was the sending unit for the fuel level, so the gauge wasn't working, you'd have to sell them a fuel pump, a filter, and all this stuff. In the past, it may have only been 30 or 40 bucks, and now it's 700 bucks plus labor. So it's not it's not nice to the consumer's wallet. So wire diagrams. Spend a minute looking at the wire diagram in this chapter. In Electude, there's another wire diagram I'm going to have you guys play around with a little bit just to get some experience with it. But wire diagrams are pretty straightforward for fuel pumps. There's really not a whole lot involved. If you've got one that's fuel pump pulse width modulated, you're going to see an ECU, electronic control unit of some kind, ECM, whatever you want to call it. Some sort of module that's going to also be involved in this. But they're pretty straightforward. There's not a whole lot to it. You've got fuse power in, you've got a relay, you've got some sort of signal that comes on at the start when they turn the key on. You close contacts and relays, you send voltage to fuel pumps, and the pumps come on. It's pretty straightforward. On your fuel pump module style that's pulse width modulated, when the power comes in to the fuel pump itself also has a module. And so that's one of the reasons they're becoming more and more expensive, is because there's some sort of brain that is controlling the pump. The fuel pump module can be, the fuel pump's electronic module, like the control module, can be internal to the pump assembly or it can be external. It just kind of depends on the manufacturer and where they put the module itself. Before I skip over to the next page, I also want to talk about this little check ball here. So manufacturers design the fuel pump with a check ball, and what the check ball in the fuel pump is for is to keep fuel in the rail. And so if you think about what has to happen, you turn the key on and you turn the pump on, the pump has to push fuel from the tank all the way up to the engine. And so the purpose of that check valve is when you shut off the car, that check valve will hold fuel from the pump to the line all the way up to the engine. So that way, every time you start the vehicle, you don't have to reprime the entire fuel system. And so if you have a check valve that goes bad, a customer complaint is probably going to be something along the lines of a delayed crank. So that vehicle cranks and cranks and cranks and cranks and cranks 3, 4, 5 seconds before it actually gets enough fuel in the rail, in the line, in order to start the engine. They're easy to diagnose. There's some diagnostic processes on it that we will discuss at a later point. So fuel filters. Fuel filters, if they are serviceable, are typically found on the fuel rail somewhere themselves. We have 3 types of fuel filters that are found on vehicles. We have the sock that's on the pump. And so if you read about that in the text, there's a first filter that sits inside the tank before the pump. And so as the pump is drawing fuel into itself, we have the first filter. As the pump pushes fuel down the rail, we have a second filter. And then there's a third filter that people always overlook. And it's either in the fuel injectors itself or it's in the fuel rail somewhere. But there's always a final screen somewhere after the main fuel filter. I've actually had vehicles that have had drivability issues where they had good fuel pump pressure and pump volume, but then the engine itself still was starving of fuel, and it was the final filters that were clogged, the ones up inside the injector themselves. So fuel pump testing. I got a video I'm going to show you guys for fuel pump testing. Most manufacturers have some means of tying into the fuel system. Some manufacturers don't give you like a Schrader valve that you can hook a gauge onto. And it can be a little bit cumbersome to try to break the fuel lines open to hook a gauge up. But watch the video that I'm going to give you on checking fuel pressure and checking fuel volume. It's fairly straightforward. You will need to have a fuel pump, a fuel pressure gauge of some kind in order to do a test like this. One of the nice things about a lot of the newer manufacturers' designs with these pulse width modulated pumps is they're incorporating fuel rail pressure sensors. And the fuel rail pressure sensor is feedback to the computer, so it knows when it told the pump, hey, put out 60 psi, it's got a sensor on the rail that actually monitors that psi, and it becomes a PID on your scan tool. And so as long as you can trust that PID, you don't even need to take out an actual fuel pressure gauge. It's always a good idea, if you're about ready to condemn a part, to go ahead and do one final check. But when you're doing your preliminary diagnostics on a fuel system, if you have a car that has a fuel pressure rail sensor on it, you can look at that fuel pressure rail sensor and you can notice right away like that it's only showing 40 psi and spec is 50. And so going into your mechanical gauge, as you're getting ready to set that up, you already have a pretty good idea what the problem is. This picture always makes me laugh, but it's actually one of the very crude ways to determine whether or not a fuel pump is working. And so if you cycle the key on, you have to have like a buddy to help you do this, because just cycling the key on, the fuel pump is only going to run for a few seconds before it shuts back off. That's part of the safety features. But what this guy's doing in this picture, I don't usually use a funnel. I'll just take the fuel cap off and stick my ear over the fuel filler neck. But if you come back to the vehicle's fuel pump and the filler neck, you can actually hear the pump if it's running. And if you've got a vehicle that's just a crank no start and you're pretty sure the fuel pump's not even coming on, it's a way to just really quickly determine whether or not the fuel pump's coming on. If you can hear it hum, then it means it's at least electrically everything is connected to it and it's turning on. It does not guarantee that the pump itself is still good. But if you come back here and you turn the key on and you hear nothing, then you know the reason the vehicle is not starting is something to do with the fuel pump itself. And then you'd have to get out your wire diagrams and verify that, you know, fuses are good, relays are good, and then finally the fuel pump is something you would test. So in illustration 19-22, zoom in on this guy real quick. What they're talking about and what they're showing you is a typical General Motors product that gives you a Schrader valve. Now, not every manufacturer gives you that Schrader valve. GM is like, just, you can pretty much guarantee you're going to have a Schrader valve somewhere on that fuel rail. And when I refer to Schrader valve, what I'm talking about is a quick connect way. It looks very similar to a tire's Schrader valve. Instead of air being on the other side of it, there's going to be gasoline, and it makes it really, really easy to hook your fuel gauge up in order to do your pump pressure test. If you don't have a Schrader valve, you can still disconnect the fuel line that comes into the rail and tee into it. And so a lot of these fuel pressure kits that are out there, they have a whole bunch of weird fittings inside of them. And hopefully at a later point in summer school here, we'll get out some of these tools and I'll show you exactly what I'm talking about. But even if you don't have a Schrader valve, you can still get into the fuel system and hook into and check and see what the fuel pressure is, which is basically what they're doing in this next illustration over here. They're teed in. So fuel pressure regulators, this is an old school design right here, real old, vacuum controlled. Manufacturers utilize a couple different strategies with fuel pressure regulators themselves. An old school design was this vacuum regulator. The vacuum regulators were awesome until they broke. And so what would actually happen is there's fuel down inside of this guy right here. So this is the fuel regulator itself. And in the book you can read a little bit more about how fuel regulators work, but basically there's a spring on the inside, and there's another picture, maybe this one's a little bit better. There's a spring in there, and the spring is set at like a certain pressure, and so fuel comes in. If the fuel pressure is too great, it'll actually push against the spring and it'll dump off any excess pressure. Well, the vacuum side of that has to do with engine load. And so if you think about it, what happens to the manifold vacuum as you take your throttle plate and open it all the way up? Manifold vacuum falls off. And so we can actually utilize manifold vacuum to determine when we need a few more psi of pressure in order to help the engine accelerate and build more power. And so rather than doing it electronically, in the early days, manufacturers just utilized the manifold vacuum as a switching mechanism to allow a couple more psi in pressure in order to allow that engine to get a little more horsepower built. And so the problem with this vacuum style is the diaphragm on the inside would actually rip. And so you had fuel down here and you had a diaphragm, just like a rubber type flap, that was sealed off from the vacuum. The vacuum would pull up on that diaphragm and basically extend the height of that spring, which would allow a little bit more pressure to be built. Well, when that diaphragm rips, on the other side of the diaphragm you have manifold vacuum. And so you could just imagine what would happen when you have a straw that is sucking fuel out of this regulator straight into the manifold. You'd have issues with anything, depending on how bad it was. You'd have cars that just cranked and didn't want to start, and you'd have poor fuel mileage issues, black smoke issues, just all kinds of things. And so one of the easiest ways to test for that is with the engine off, pull that rubber hose off, and if fuel comes out of there, you can guarantee that that regulator itself is bad. It's a 100% foolproof test. And so another thing you can do to see if the regulator is working, it could get just stuck. And so maybe you have a customer that's complaining of a poor fuel mileage issue because it did move to the higher PSI setting and it never came back. And so now at idle speeds or light cruise speeds, you have too much fuel pressure. One of the ways you can test for this is when you're watching with your fuel pressure gauge hooked up. When you pull that vacuum hose off, you should see fuel pressure fluctuate. It should come up a few psi. If you pull that vacuum line off and it doesn't move on your fuel gauge, pressure gauge, then you know that that regulator is bad. So the final thing I'm going to discuss here, and I'm going to do a little drawing as well, but fuel pumps and current. So the relationship between fuel pump being on and the amperage that it draws. Most fuel pumps will draw 10 or less amps. There are specs that are out there. You can find this stuff. Your typical naturally aspirated engine, you know, just little economy 4-cylinder engine, the pump's probably only going to be drawing about 5 amps. They don't work. They're not that big of an electrical component. They're not a starter motor that's drawing 150 amps. And so one of the things that happens with electric motors as they fail is they start to draw more and more current. By design, they'll just draw more and more current. And so if you have a vehicle that is struggling to build fuel pressure and you're suspicious that it's a fuel pump, you can actually just clamp an amp clamp over the wire that runs the fuel pump. You could do it in the fuse block. You could do it at the relay itself. You can make a little jumper that comes out and clamp your amp clamp over it. This illustration, when they're actually connecting through, is not a good idea. The fuse link in your multimeter is probably good for 10 amps or so, and in most cases your pump is not going to draw more than 10 amps, so you don't have to worry about breaking the fuse. But let's say you have a vehicle that has a bad fuel pump. You're going to find out two ways. You're going to find out you're going to get a momentary flash probably on the screen of 11 or 12 amps, and then the meter's going to go dead. And so you have to be mindful of that when you're doing your current draw testing. You want to make sure you're doing your current draw testing with an amp clamp, and you're not actually a part of a live circuit with your multimeter. Now, on the better way to do this is with a Pico. And so Pico oscilloscopes, or just an oscilloscope in general, will actually graph out the armature windings. And so there's a lab that I would normally have you guys do, and we will do this at a later point, but let's say I have just a meter, and let's do 10 amps on the tall side, 0 amps on the low side. When you graph with an oscilloscope, you can actually see every armature winding. And so what you want to see is a normal on-off pattern. Every time you see a spike up, the pump has energized and it's moved. And then as you see the waveform drop down to 0, it's at the off point. And so it's between armature points. And this pump is, as it spins, it's going to create a signature that looks like this, or something like it. If you have a pump that has a bad spot in it, you will actually see the downward spike and then a gap. And it might not look exactly like this, but it'll be pretty obvious to you that you are missing something in your fuel pump signature. And it will repeat every time you get to that bad spot. And so I have a video that I'm going to show you on this as well, doing a current ramp test, but with an oscilloscope on a fuel pump. So a typical pump that has this type of signature to it will be one that you have to smack the fuel tank in order to get the pump to come back on. And believe it or not, that actually does work. It's not a made-up fictitious tale. I've done it multiple times in order to get a car to come into the shop, like in order to drive it into the shop. So what you'll have happen is a customer will shut the car off, and it's always at the gas station too. So it's always, they just fill the tank up. But they'll shut the car off and they'll find that bad spot. The armature will stop on the bad spot, and they go to start the car and it can't get started. The pump can't move because it's in the off position. And so what you can do is you can actually smack the bottom of the tank while the key is on, or while you're cranking the engine, and you might be able to jar that armature just enough to get to a good spot to where it can take off. And as it is running, the simple centrifugal motion of that pump will allow it to skip past the bad spot. Now, that doesn't mean it'll stay running forever. It could get hot and something can open up and it could stall out again. But I've done that several times in order to get a car in the shop, so I don't have to push something in, like a big truck or a big van. You got to get everybody on board with you to push it in. It's always after they fill it up, though. It's like every pump that goes bad. I don't know what it is. But there's also a few things you can do with oscilloscopes. I'll show you, but you can actually watch for armature specs that come too high, like above, or maybe you get kind of like a up down. It kind of comes down and then it goes back up, then it comes back, like a really obscure looking waveform. There are technicians that will do an oscilloscope check on fuel pumps as part of like a good thorough vehicle inspection. So if you have a customer that comes into the shop and they're going on vacation later this summer, and they want you to look the car over before they go drive to Florida, it wouldn't be a bad idea if you had an oscilloscope to just go ahead and check it. You can pop out a relay and you can put a jumper wire in, you can clamp over it. You can set this test up in about 2 or 3 minutes. And if you see an armature waveform that looks kind of funky, you could at least warn them. If they don't want to replace the pump now, you could at least warn them that the pump might actually fail on their road trip. And believe it or not, but you can actually pick out fuel pumps as they're about to die before they do die, if you know how to use an oscilloscope test. And so we will get to that, and we will do a test like that at a later point. So I guess go ahead and watch the videos that I have, do the Electude assignments, and as always, get a hold of me with any questions you have.